some of the things I'm going to talk today are a little bit out of the realm of your primary interest, but hopefully there's enough overlap that you'll learn something. So we've talked about so far that dredging is expensive. We've mentioned a little bit that it has environmental consequences and that it can be difficult. What we're going to talk about for the next couple of minutes is the idea of using measurements and science to help with cost, to help with the difficulty, and to help with the essentially the overall performance. Because the key thing in doing dredging is to do it right. If you do it right, it's efficient, it pays for itself, and it pays for itself throughout the life cycle of the project. So we're going to start with a video here. Essentially, this video is an explanation of the purpose of the harbor deepening project. Container ships provide essentially about $100 billion throughput to the Port Authority every year. That's a considerable amount of money. And these ships are getting deeper and deeper. The 6th generation ships that you're seeing here are essentially require a draft of 48 feet. And the harbor, as Lisa mentioned, has progressively increased in depth. And recently it's been 42 feet, now it's going to 50 feet. The key thing is we need to be able to bring them in. To bring them in, the harbor needs to be deepened. And what you're going to look at, this is Port Jersey, which is a little bit south of Staten Island. It's in Bayonne. And there's a, can I pull this thing a little bit? There's an excavator, an animated excavator here that was used to deepen the harbor. Material is withdrawn from the subsurface, put in scows, and taken to various disposal sites. So, sustainability. The issue with sustainability is essentially 2 things, or the things we want to address today. Which I do back up. I don't have enough length in my... Is this okay? The 2 issues are, 1, intelligence, which I'm going to claim is basically mapping, and the second is forecasting. In forecasting, the key element of forecasting is complexity. We'll talk a little bit about that at the end. A lot of the discussions we talked about in terms of scale, we talked about in terms of river behavior, et cetera, have to do with complexity. Sometimes making simple assumptions and simple models just doesn't work. And we need to talk a little bit about that. All right, so this is Newark Bay, which is an element in New York Harbor. And what we're going to do is we're just going to roll the water back, and I'm going to show you this little section right here, which is the bottom of Newark Bay, the entrance to Kilburn Cove. And what that looks like on the bottom is something like that. So that's an acoustic image of the bottom. The black material that you see in the lower corner here is recent silt. The material that you see in the middle is rock, and that was recently dredged material. Now this image is probably 5 years old. All this material has been removed, all this material has been removed. But the point is that we can see teeth marks from the dredge on the bottom. We can measure the thickness of the sediment, we can measure the top of rock. These are sedimentary features on the bottom. This is an acoustic image of the Hackensack River. You can see the sedimentary structures, you can see scours, etc. Oh, the thing on the left is a compass. Every time you see a compass, this is a map. And every time you see a plumb, that's a cross-section. This is Arthur Kill. You can see in Arthur Kill that essentially the light material, this is a sonic reflectivity. The lighter color actually represents harder material. The darker color represents softer material. The softer material is the silts that we talked about earlier today. So this is what it looks like in 3D. The two grooves you see are basically pipe tracks. Pipes sit in those trenches and go across the channel, and the silt is confined in the edge. So why is this all important? As you go and dredge, you have various complications. You have rock, you have utilities you have to avoid, you have obstructions you need to avoid, and you need to be able to separate the various types of content, various types of sediments that you're dredging, because you need to estimate the cost of removing and disposal. So having a good idea and intelligence on mapping of these materials beforehand allows you to control costs. This is a cross-section, so the plumb is on the left. This is depth on the left side. That's rock. It's about 100 feet from top to bottom. So you've got about 70 feet of sediment on the left, on the right and left. In the center, the rock comes to the surface. So with this measurement, and I'm actually going to put this down. This area right here is essentially this image. So the detail, that small image ends up having this kind of detail in it. You can actually see the foresets and bottom sets in the sediment. Why does this matter? Because we can actually map the rock to within, say, the order of a foot throughout the entire area, get the estimates right, the bids are better, the construction is better, the result is better. The coloring on the bottom is again a cross-section through the area of the work. Red means hard, yellow means softer. So the red material is very hard to remove. This is a cross-section in the Arthur Kill, where the red material is essentially rock and the blue material is sediment. You can see the rock is stratified to the west. The yellow material can be dug, and this is what the material looks like when it comes out. Pipelines, we're going to skip that. All right. So mapping is essentially a relatively simple problem. Simple problem being something like baking a cake. A complicated problem is like putting this various number of steps together, such as going to the moon. But then there are complex problems. Complex problem is equivalent to, say, raising a child. Forecasting is equivalent to a complex problem. So here's an example. We think of sedimentation in terms of sedimentation rates. What's the sedimentation rate in New York Bay? What's the sedimentation rate in New York? This is a dry delta. This is the Niels Delta in Australia. Essentially, every one of the objects there was produced in a different storm, or in a different year, or in a different flood. So, scale. What you have at the bottom is wave number. It's the inverse of wavelength. What you have on the left is frequency. That's the inverse of time. In the upper right-hand corner, you have molecules moving very fast. In the lower left-hand corner, you have continents moving extremely slowly. Point is that sediment on a second-to-second basis moves at water speed, roughly. That speed, any slope on that plot, by the way, in a frequency wave number plot is a velocity. Any change in slope is a group velocity for any of those who care. The point of it is that sediment moves on a second-by-second basis at water speed, but the deposit moves extremely slowly. So the larger the object, the longer the time, the slower the sedimentation rate. So if you make a sedimentation measurement, say on the order of a day or a month or a year, and you need to take that to the century or 10 years or the life cycle of the asset, you have to make a correction based on the scaling necessary. So what am I talking about? I'm talking about singular events. So this is, tomorrow you're going to go through Rockaway Inlet, Marine Parkway Bridge. Marine Parkway Bridge this is essentially one of the Development Submarine Parkway Bridge, and the image on the right is basically a statement about or a measurement of the piers below the bridge. The key issue here is that there was a great deal of concern that erosion that might occur in a hurricane could, in fact, expose the piers at the base of the bridge. Mathematical models based on simple multiplications predicted that a hurricane could produce an erosion on the order of 150 feet deep. It is presently maximum 45 to 50 feet deep underneath the bridge. However, geologically, one can demonstrate that the Holocene-Pleistocene boundary is at 67 feet. That means over 7,000 years, there's been no erosion greater than 67 feet. Therefore, one has to be extremely careful with extrapolating simple ideas with regard to estuaries, rivers, anything else, and extrapolating them and making decisions on them without understanding the humility necessary in terms of taking care of complex problems. I have one minute just to point out, not everything in dredging is the harbor deepening project. This is a little dam in Vermont. It has accumulated sediment over the years. That's the dam. Its low-level outlet right in front of you looks something like this. That gate was sedimented in, and essentially this is what the structure looked like. The important thing about this is that the sustainability of it is that this project was done for half the cost because they were able to go down and, if you will, surgically remove the material while preserving the low-level outlet and not damaging it. So in conclusion, there are two parts, we think, to applying science in a sustainable way, or in a way to create sustainable engineering in dredging. One is to map and monitor. The second is to employ a degree of humility when we forecast, and to recognize that those models need to be developed which understand, one, the scaling involved, and two, the importance of singular events. Thank you.
I don't know why you thought that would be outside of people's zones of interest. That was fascinating. Those images are unbelievable. So we're not doing a panel at the end of this section. What we're going to do instead is do just a couple of minutes of quick Q&A for each speaker right after they talk. So surprise. Does anybody have any questions or something you want to talk to Bill about?
Yeah. I was interested that you showed the dam image at the end, and I guess I'm just curious if you see in one of the rising issues is sedimentation behind things like Hoover Dam or in Glen Canyon Dam and so on. And I guess I'm curious about work there as far as building geophysical imaging and also how that's going to be dredged to save the dam.
So I guess I got to use this. And I really apologize for not being able to handle this thing. Yes. The measurements that are usually made for sedimentation are bathymetric measurements. You make a measurement, say 1990, and then you make a measurement 2000. And then you make an extrapolation of how fast something's silting in. And that's what I'm referring to, is that you have to be careful. You have consolidation going on, and you're also filling spatially in different areas. I would contend that while years ago there was a great deal of interest, I think, in removing dams, there's a renewed interest in utilizing reservoirs, obviously, and utilizing reservoirs for local energy. So I think there is an expansion of interest in using technology to do this because it's expensive to do. So I don't know specifically about Hoover Dam, but I am aware that locally, meaning sort of the northeast through to, let's say, Ohio, there's a great deal of interest in reservoir cleaning, reservoir maintenance, cleaning the facilities. I mean, that dam there was probably 150 years old. So.
We've got time for one more if anybody else
have a question about, just about like public access to the information that you have. Like we're living in this world now where satellite images are available all across the globe for multiple years. Do you see the kind of underwater realm opening up as the next open source map of harbor battle?
So it's very interesting. That's actually, okay, there's several kinds of studies, right? If studies done for the government, that information can be made available to you. Studies done for a private entity, that study it then belongs to the person that paid for it, depending upon the contract, but that's the way it is. I suspect that most people find that the more information that the public has about the reality of the natural system is a benefit to both sides. In other words, what I think we found is that agreement is much more easily reached when you're talking about data as opposed to when you're talking about something that you're just sort of waving your arms about. We would very much support access, and in fact, it's just a matter of time being able to get it out, being able to make the measurements, making it available. We're very much in support of that. Again, everything has to do with cost, because not only do you have to archive the stuff, keep it, then you've got to put it out, make it available. So it's a matter of making it commercial, I think, to make the thing fly from that point of view. But this data, I would say half of what we have here is freely available through open source. So, and if you're interested in any of the studies, you could always ask. We can always send anything out. So, yeah, thank you.
Okay, thanks.
Thanks very much.